Okay, so let's get started. We're going to be taking a look at setting up and working with our standard style knock control with PCLink G5 and G4X programming. Now there's two different methods for knock control that we can implement with our link. There's a standard style, which is kind of more of the old school traditional knock control routine that most standalones have. There's nothing wrong with it. It works really well. In fact, it's my go-to choice for working in the knock control. But we also have another method called normalized knock. We'll be taking a look at that in a separate tutorial because it is pretty different or substantially different than what we have in the standard style knock control. So we'll get into that later. We're going to be dealing with, again, the more of the kind of the traditional style knock control here in this training module. So we're going to be exploring how to set it up, all the settings and configuration details to make things work. And we'll take a look at just one or two basic data logs so we can make sense of how to interpret a data log to see if we have knock or not and how the system actually works. Now, the other thing I want to talk about here before we jump into working in the tables, going in and setting up the knock control and making it active and starting to try to work with the system, I want to talk about some of the basics here. So what is a knock sensor? So a knock sensor may or may not be fitted to your engine. Most OEMs will have a knock sensor somewhere on the engine. So typically mid to late 90s engines and on will have a form of a knock sensor on the engine. The knock sensor is a piezoelectric circuit. So what that means is it's going to be translating pressure ripples that come through the block when we have a really high cylinder pressure spike when a knock event happens. It can translate that pressure ripple into the sensor, and then the sensor is going to output a voltage scale. A larger knock event will have a higher pressure ripple and therefore a higher voltage output from the sensor. A small knock event is going to be something that it probably is going to pick up, and it's going to be a lot smaller of a voltage output. So we have a kind of a proportional output from the sensor based on how large of a knock event that we had, again, in that piezoelectric circuit. So it's translating a pressure input to a voltage output. Now, when we're talking about our knock sensors, there are two types of knock sensors you'll find. There's a single wire knock sensor and a dual wire knock sensor. Most OEM engines will be fitted with a single wire resonant style knock sensor. Now, a resonant style knock sensor differs from a flat response sensor, that's the two-wire sensor, because it's tuned to the frequency for when knock happens in a particular engine. So an OEM is going to essentially calibrate that sensor to the engine. Now, it has its advantages and disadvantages. One disadvantage is that the output, the amplitude output, is usually really choppy and sometimes unreliable to see if we have knock occurring or not. Now, a two-wire sensor is what's known as a flat response style sensor. They're typically Bosch is the manufacturer for most flat response sensors. Most modern, so newer, 2010 and newer, for example, a lot of engines will be fitted with a Bosch style sensor. The part number on that sensor is 0261 231 188. So that's the Bosch flat response sensor that I typically always run if I'm retrofitting a knock sensor to the engine. That's the part number I use. It's relatively inexpensive. Last time I checked, they're about $20, $30 on Amazon. So inexpensive to add a knock sensor to the engine, but invaluable for allowing us to do our calibrating and tuning work. So if you have a resonant sensor, let's say a Toyota 2JZ engine, those came with two knock sensors, and they're both single wire resonant sensors. They can be used for knock control, but be aware that the amplitude output sometimes is really choppy. We'll actually take a look at a 2JZ VVT-I engine with a factory resonant style sensor here in a data log example in this training module. You'll see what I'm talking about. Really choppy in terms of the output. If you have an engine with a two-wire sensor, great. You'll have a little bit better signal amplitude output, so signal to actual knock event output, meaning the sensors are relatively quiet in the amplitude, and when the knock event happens, it's usually a relatively large spike, and it's very distinctive, so we know when a knock event happens or not. So the resonant sensors can work, but the flat response sensors are the preferred way to actually monitor knock. So you could always retrofit a knock sensor to your engine. Not a big deal if you have, again, no knock sensor, or if you have a resonant, you can actually replace the resonant sensor with a flat response two-wire sensor. In order to wire it, it's pretty simple. One wire is going to go to sensor ground. The other wire is going to come right back into the knock input to the ECU. So you don't want to chassis ground that sensor. You always want to sensor ground it to the link so it completes that circuit. pretty easy to wire in, again, pretty simple and straightforward, but that Bosch part number works well. Now you don't have to worry about if you've missed that part number. I actually have it documented here in Excel spreadsheet we're going to talk about here in this training module, so you'll be able to source that particular part number in this the Excel spreadsheet we have here for the training course. So yeah, no panic as I just read that Bosch part number out. Okay, so now we went some of the basic background details between resonant, flat response sensor, and then understanding what the actual knock sensor does in terms of the actual functionality. It's going to be telling the link when a knock event happens, and we're going to get a 0 to typically 5 volt output from the sensor proportional to the knock event. So we'd like to see when knock happens, we'll have a nice large rise or a spike in the signal that signifies that something happened there, and we know when the knock event happened at. This actually aids us in 2 different ways. So one, we know when we're pushing things too far in our main spark timing table. If we flip over here to our spark area here, we've talked about the main spark timing table. So when we're trying to dial this in, we're always trying to reach maximum brake torque. Now, you don't necessarily need a dyno to figure out if you're getting close to maximum brake torque, but it's definitely ideal to be able to watch the torque output out of the engine as you're trying to advance the timing here and try to figure out what is the most optimized spark timing for the engine that you're tuning. Now, we can use a knock sensor to tell us when we have pushed things too far for the actual spark timing. So we may not exactly be able to determine maximum brake torque if we're reaching it or not without a chassis dyno, but we know without a dyno if we're getting knock and if the timing is too advanced. So one huge benefit of running a knock sensor is to be able to monitor what's going on in a per cylinder basis. You can actually see in each cylinder if there's a knock event happening. Thanks for checking out our teaser clip. If you want to see the rest of this video and more than 500 hours of current EFI training we have to offer, make sure you click right here. If you want to go and check out more teaser clips from this training course, click here, and you don't want to miss any of the videos we're going to be releasing on this channel, so make sure you subscribe and click here. Thanks for watching, and I'll see you guys later.